All right, so let's explore this idea of these partial sums a little bit further in this example. Find the first four partial sums and the nth partial sum of the sequence given by. All right. So I guess I need to find the first few terms. So the first term is going to be 1 over 1 minus 1 over 2. The second term is going to be 1 over 2 minus 1 over, I might have said times, I meant minus. Now you might say, well, you should be simplifying this and combining it and stuff. And I think you're going to maybe see that sometimes simplifying it maybe isn't the best thing to do. But this would be a 1/2. And this would be, I don't even want to do it, I guess. 3, 6 minus 2, 6. 3, 6 minus 2, 6. 1/6. I think you're going to see that we maybe don't want to do that on this one. So let's just leave it. So this is going to be, I'm plugging in a 3 for n. 1 over 3 minus 1 over 4. And a sub 4 is 1 over 4 minus 1 over 5. All right, so let's find the first partial sum. The first partial sum is just a1. That is 1 minus 1/2. All right, that is 1/2. The second partial sum is a sub 1 plus a sub 2. That is 1 minus 1/2 plus 1/2 minus 1/3. Maybe I do want to keep that like that. I don't know. Let's see. We're looking for patterns here. That's what you're always trying to search for here. As you can see, these 1/2s, I got a plus and a minus, they cancel out, so you just get 1 minus 1/3. So 1 minus 1/2 is 1/2. 1 minus 1/3 is 2/3. Okay. S sub 3 is going to be a1 plus a2 plus a3. That's going to be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. A, 1, 2, and 3. So now these cancel out, those cancel out, and you just get 1 minus 1/4, also known as 3/4. S sub 4, a1 plus a2 plus a3 plus a4. I think you guys are kind of seeing the pattern here. I think these are called a telescoping sequence or telescoping series. I think. I'm not even really sure. Sorry. But basically, you're kind of getting the inside terms to cancel out. Cancel, cancel, cancel. 1 minus 1/5, which is 4/5. So here's my sequence. Oops. Here's my sequence of partial sums. So now I'm looking for a pattern in my sequence of partial sums. So I listed the first four. Those are the first answers. And then the nth partial sum. So what's the nth partial sum? Well, it looks like I'm going 1 over 2, 2 over 3, 3 over 4, 4 over 5. It looks like the top number is just always your n, 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 n. And your bottom number is always one bigger than n. That's the nth partial sum. And again, we're not really going here now, but if you were to add, if we were to take this sequence of numbers, a1 plus a2 plus a3, and add them forever and ever, infinitely, this kind of tells you what that infinite sum is approaching. As n approaches infinity, what does this get closer and closer to? Well, what kind of number do you get if you have a trillion, like a quadrillion, some huge number over another huge number that's just one bigger? Well, this number is getting close to 1. So what that tells us is this infinite sum is approaching 1. Or if you can imagine adding all infinite numbers, it would be equal to 1. Okay? Again, we're getting a little ahead of ourselves, but whatever. That's why we're doing these stupid partial sums anyway, right? Write each sum using summation notation. So these are a little challenging. You need to use, summation notation, I equals something to something of something. So we're trying to write down this finite sum in a shortened form using this notation here, okay? So this is going to be my, kind of looking for the closed form, the explicitly defined formula for the sequence of these numbers. Now there's a sum, but what, the numbers, the terms. So this is n equals 1, n equals 2, n equals 3, n equals 4. It looks to me like if you take 2 and you square it, you get 4. 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared. So it looks like we're adding up from I equals 1 to something of I squared. 1 squared, 2 squared, 3 squared, all the way up to this number here. Well, what number would that be? I squared is equal to 10,000. Square root both sides, plus minus, so I has got to be equal to, looks like this plus or minus 100 times 100. So that's plus or minus 100. Obviously it's got to be positive. In fact, if you wanted to do this sum, even with a calculator, right? Let's say I gave you a calculator and I gave you this problem on test and said evaluate it. You wouldn't really want to type in all of these numbers. It would take you forever, take you a long time. But if you can write it in summation notation, you can type that into the calculator very easily. So that again is something you might see on the calculator portion of the test. Hit this little button here, do our little summation. I equals 1 to 100 of I squared. Calculators are great at these things, right? I would never want to do that thing by hand, but it looks like it's 338,350. Okay? All right. But they didn't tell me to put in a calculator, they just told me to write this. All right, so here I got another sum of numbers. Again, I kind of want to think of this. I want to kind of find the A1, comma, A2, comma, A3 when my numbers are 1/5, negative 1/6, positive 1/5, 1/7. So I want to find a closed form for this sequence that I'm adding together here. So this is n equals 1, n equals 2, n equals 3. For me, I always want to see these numbers. In fact, I should rewrite this so I can spread it out and see it a little more clearly. I want to associate, not, when you look at it, you always want to say, just add 1, next one's 11, next one's 12. Well, yeah. But how do you use these numbers to generate those numbers? That's what an explicitly defined formula is. So my A sub n, if this was a sequence, looks like I'm adding, I just take 1 over, and then the bottom, it looks like I'm just taking my n, I'm adding 4. 2 plus 4 is 6. 3 plus 4 is 7. 4 plus 4 is 8. But I got to get these alternating signs. And if you remember from earlier on in the chapter, to get the alternating signs, you multiply by negative 1 to the n power. Or n plus 1. Let's see here. If I put a 1 in here, I raise it a negative to the 1 power, it's going to be negative, so that's going to make the first term negative. Nope. I want the first term to be positive. Let's try that. If I put a 1 in there, I get a 2. Negative 1 squared is positive. All right, that's good. If I put in a 2, I get a negative. So there it is. This is how I generate these terms. So my sum is just going to be the sum from I equals 1 to something of negative 1 to the n plus 1 over n plus 4. I just need to figure out what the last term is. What is the n value that corresponds to that last term? Well, this is 1 over n plus 4 equals 1 over 50, right? I think this should technically be a negative 50. I think it was a typo. Whatever. So it looks like my n should be 56. sorry, 46. I put a 46 in there. On the bottom, I'm going to get 46 plus 4, which is 50. So there we go. Okay. All right. And that's it.